So let's continue our discussion of the propagation of mechanical waves. So we're going to examine how these mechanical waves are formed. So we're going to look at the source of mechanical waves, and then we'll examine several important physical quantities that help us describe the way a wave moves. So let's begin by examining the following diagram in which we have the formation of a mechanical wave. So let's suppose we take an elastic cord that is stationary and lies along a horizontal axis, let's say along the x-axis. Now in diagram 2, let's suppose I take one end of my cord, say the right end of my cord, and I create an up motion. So as I create that up motion, what happens is the adjacent molecules that are located inside the cord found next to the hand also move upward with a velocity that points in the same upward direction as my upward motion of the hand. Now when I make that upward motion, I then follow by a downward motion. And when I make that downward motion as shown in diagram 3, the adjacent molecules found where my hand is then move downward. Now because there is a downward force here, there is a upward force on this side, and this upward force creates a velocity of this section that now points upward. So before, this section was stationary, but because I created that downward force, what happened was now these molecules are moving up. So these molecules are moving downward, these molecules are moving upward, and this entire crest, as shown in diagram 4, will now propagate in the negative direction along the x-axis. And this crest will continue to move until it reaches the end of the cord. So once again, in diagram 1, we have a stationary cord. In diagram 2, we take our hand and the hand pulls on the right end of the cord, and this creates motion. Now in diagram 3, adjacent sections of the cord feel the same force, but now the force points in the opposite direction as this force, and so these molecules move this way, these molecules move this way, creating the following crest. So as succeeding sections move, the wave crest moves, propagates outward in the negative direction along our x-axis. Now, this quick up and down motion of the hand, which creates a single wave bump, is known as a pulse, which is really a vibration or an oscillation. So the creation or the source of a mechanical wave is simply a vibration or oscillation. In this case, the vibration was a result of our hand that moved our cord up and down. Now, what exactly is a continuous or periodic wave? Well, a continuous or periodic wave is a wave that has a periodic or continuous source of vibration or oscillation. So basically, if I take my hand and I continue moving my hand up and down with the same exact pulse, so each pulse has the same exact time interval, then that means my source of vibration will be continuous. And if the source or the vibration obeys simple harmonic motion, so if it's continuous, that means the entire wave that is propagating outward will also experience simple harmonic motion. It will also be sinusoidal in both time and space. And this is assuming that the medium through which our wave is traveling is assumed to be elastic. So let's examine the following curve. Let's suppose we have a continuous movement of our hand up and down. This creates our crests, and we have the following result. So this portion of the wave is known as a crest. This portion is known as a trough. Now, the distance from our equilibrium position shown by this arrow to our crest, or the distance from the equilibrium position to the trough, is known as the amplitude of the wave, given by capital letter A. So capital letter A is the maximum height of the crest, or the maximum depth of the trough relative to our equilibrium point, this black line as shown. Now, the distance from one position on the wave to a second position on the wave, where the wave begins to repeat itself, shown by the Greek letter lambda, is known as the wavelength. So for example, from this position to the next position where it begins to repeat itself is known as the wavelength, and this is usually given in meters. Now notice, if we choose this position, then the wavelength is simply from this position to the next position where it begins to repeat itself. So if we want to go from one crest to the next adjacent crest, this distance is also our wavelength, given by the Greek symbol lambda. Now, the frequency given by a lowercase f is the number of cycles that are completed over some given period of time. And the frequency is given in cycles per time, so cycles per second. Now, what about velocity? Well, v, or the velocity of the wave, is simply the velocity at which the wave crests are traveling in the forward direction. So our mechanical wave in this example is moving in the positive direction along the x-axis, but the individual molecules are oscillating with a velocity that either points upward or downward, as shown by the following green vectors. Now, if we take the lambda, if we take the wavelength, and we multiply it by the frequency, that will give us the velocity. Or equivalently, if we take the lambda and divide it by the period given by t, that will also give us the velocity of our wave. So for example, if our wavelength is 10 meters and it takes the object 10 seconds to move this distance, then that means 10 meters divided by 10 seconds gives us 1 meter per second. So the velocity of such a wave is 1 meter per second.